Then I would like to discuss some theoretical result concerning inverse Faraday effect in superconductors, and how we can generate the different current carrying state in superconductor and perform switching between different current carrying states with 100% probability. Then I will start with vortices. It's microscopical object. In fact, has been discovered theoretically by Alex Abrikosov more than now 70 years ago, a long time ago. And in fact, vortex is a tiny object which carry one flux of the magnetic field. And at the center of the vortex, superconductivity is destroyed, and current, superconducting current, circulate around it. And sometimes it's called fluxon, mainly in the situation when it's some nanoscopic size of the superconductor, and it's less than 1 London penetration depth. And the first experimental observation and confirmation of vortices has been obtained by magnetic decoration technique, the first vortex lattice observed. Now there are much more sophisticated and exact method like squid imaging, nanosquid imaging, or STM imaging of superconducting vortices, which can even permit us to look what happens in the core of the vortex, in the central part when superconductivity is destroyed. And magnetic properties of vortices are well known, but in fact it has been predicted that also Abrikosov vortex can have an electric dipole moment. And the reason is very simple, because at the center of the vortex, superconductivity is destroyed, so the energy of electrons is somewhere higher than in the periphery when the coupling is existing, and is coupling, superconducting coupling naturally decrease energy of the electrons. So we may expect more electrons outside the vortex core, and this redistribution of the electric charge will create electric field, and in fact which correspond to the dipole electric moment. And up to now, in fact, this has not been confirmed directly. There are some indirect hints about this, but direct observation of the electric dipole moment is lacking. And in our team in Bordeaux, which work in photonics, the very sensitive technique has been developed. Namely, it is the spectroscopy of single molecules. It's single molecules. Normally, it's some organic molecules, and it occurs that fluorescence signal, for example, for some dilute solution of these molecules on the surface, each molecule is in somewhere different neighboring position, and it has his own frequency of the fluorescence. And so you can separate the frequency response of single molecules, and then to observe the influence, for example, of the external perturbation, like electric field, or in microscopical also electric field inside the sample on this molecule. So in some sort it's nanoscopic electrometer. And the idea was to use this technique, to put these molecules on the top of the vortex, for example, and to observe the dipole moment, electric dipole moment of the superconducting Abrikosov vortex. And the first experiment has been performed, but naturally, because it was optical laboratory, also it was interesting to observe where vortices are situated, and for this, also it was quite convenient to use, once again, optical method, and more precisely, it's a Faraday rotation. It's magneto-optical imaging of the vortex through Faraday rotation. If we have linearly polarized light, when it goes through the region, namely when vortex is situated and magnetic field is present, due to Faraday rotation, the polarization change its direction, and then we normally it's reflected also, so it goes through 2 times through the region when we have magnetic field, and we have rotation of the polarization in the region when we have magnetic field, and no rotation when we have no rotation. So after this, using polarizer, we can obtain the image of vortices. Well, known technique, more or less standard one, but quite convenient for optical approach. And the first experiment to look on this electric charge were quite, let's say, interesting, because we thought that we observe the effect, the electric field of the vortex, but the first experiment were performed not on type 2 superconductor when we have vortices, but type 1 superconductor when in fact instead of vortices we have intermediate state when we have the sequence of normal and superconducting region. But once again, due to this redistribution I mentioned, due to different energy condensation, we may expect the appearance of the electric dipole moment and the interface here. And indeed, this single molecule technique reveals the signal. So it reveals the existence of the electric field, electric dipole moment. So all team was happy, but after that they decided to do the control measurement, and they withdraw the magnetic film. Magnetic film, it's a garnet, it's ferromagnetic garnet, has been used just to visualize the distribution of the magnetization. Yes. And when magnetic field was withdrawn, but in such a case, the intermediate state should not change. It simply was used to visualization. For example, here it's a normal region, it's superconducting region. And the effect has disappeared completely. And after some more in-depth investigation, we realized that, in fact, what has been observed, not this electric dipole moment at the interface, but also pretty interesting effect. It is a so-called flexomagnetoelectric effect. Due to non-uniform magnetic field, magnetization in the garnet also changed in space, and this variation of the magnetization induce electric moment. So it was flexomagnetoelectric effect. And it was interesting that one of the rare direct observation of this effect on the microscopical level. But nevertheless, the main goal was not achieved, and the reason we start to think why we did not observe the electric field of the vortex, and in fact it's decay very quickly with the distance, and the most plausible explanation that the vortex is rather far away from the molecule, because these molecules are redistributed on the surface, and after that they are frozen. You cannot change their position. And you can concentrate on one molecule, but in fact you don't know at what molecules you are concentrated, and you look at signal. But what you can move vortices. So we decided just to try to approach vortex to these molecules and to increase in such a way the signal, because everything was at the limit of the sensitivity of the technique. That's why we decided to look how we can move vortices. And in fact, it exists several possibilities. The most, let's say, direct and well-known, it's to use magnetic force microscope. First of all, we can observe by this microscope magnetic field of the vortex, but also you can, because it's magnetic tip, you can drag vortex, and so you can move vortices, and like that, for example, some writing with vortices has been performed. And also you may use squid microscopy with some additional coil, and also...
Why not FR?
Not?
SU.
What does it mean SU?
SU? Naturally, what people write when, what is this, when they obtain something, the name of their university to obtain more funding.
Yes, yes. So which one is it?
So it is South University or Southwestern University, something like that. Yeah. It's quite natural to attract, to have the magnification effect. Yeah. Now you can imagine whatever you want. Okay. But I'm 100% sure that it is their funding body. Yeah, who provide money. Okay. Another possibility is strain-induced microscopy, also putting touching the superconductor, you can move vortex in the strain. But all this technique, in fact, is rather time-consuming. It takes a lot of time to write these letters. And we decided to see if it's possible to use, because once again, everything happens in optical laboratory. Is it possible to use focus laser beam to move vortex? And the idea was very simple. If we hit locally superconductor, in such case, the parameter which determine vortex energy, and its well-known formula is square of the flux quantum divided by the square of the London penetration depth. But London penetration depth, with increasing of the temperature, increase. So, because it's go to infinity at transition temperature finally, yeah? And it means that at the region when we hit superconductor, the energy of the vortex will be smaller, because it's in the denominator. So, in fact, hitting superconductor, you attract vortex due to the decrease of the energy to the region when temperature is high. So you can, like that, trap vortex and drag it if, naturally, the thickness of the film is rather small. And now I can show you, it's an experimental setup, but as I'm a theoretician, I just will say only 2 words about this. It is the lamp which produce polarized light to observe vortices due to this Faraday equation, and the laser beam to produce hot spot. And then you manipulate vortices with this hot spot. And for example, it is a result of experiment in thin niobium film, approximately 100 nanometers thickness. And magnetic field is pretty low, just comparable with the Earth's magnetic field. And we can see here some sort of the random distribution of the vortices. And now, with the help of the vortex beam, you can move these vortices, and you can write with these vortices, in fact, something And here what we choose to write AV, Abrikosov vortex. And by this time, Abrikosov was still alive, and we sent him a Christmas card, right? Written with vortices. Huh? A little bit with binocular, because he used last time, he used a huge screen of the computer, and with magnification, he could read. But also not very quickly. Well, and like that, naturally, you can, for example, to drag vortices and to manipulate them, to write something. And, for example, you can, if you have dense vortex structure, here density of vortex is very large, with laser beam, you can, for example, to free some region from vortices. It's some sort of the brush, of laser brush. And it may be interesting for some application because the presence of vortices produce some noise. Okay. Another, we may say why it's important to, yeah?
I wanted to ask about the detection. So the detection of the field is done by a molecule?
No, forget about molecules. Yeah, yes, it was motivation.
No, but the detection, is the technique sensitive enough to detect one molecule, changing the spectrum of one molecule? Because
In principle, yes. So if you have single molecules and vortex just underneath, it produce something like 1 dB electric dipole moment, and it's quite enough to shift the spectrum of fluorescence.
but you can measure only one molecule, because only one molecule.
Yeah, yes, only one molecule. Yeah. Because in fact, from a practical point of view, what happens? The experimentalists put some dilute solution of these molecules, and then they use a laser beam. But in sport of the laser beams, around typically 200 molecules. And so you have 200 different spectrum. But fortunately, due to different neighboring, each spectrum are individual. And so after that, you can concentrate on one spectrum and to apply some external perturbation and to see, to use it like electrometer. It's good that you answer this question. And finally, the task to see this electric dipole moment is still unresolved. It's continued, but on the way we obtain some very interesting.
Also, another question, why did you do it in niobium? I mean, there the electric charge should be very small, no? Or
Yes, yeah, indeed. It's also a very good question. The choice of niobium because it's technologically more appropriate. But much better would be high TC superconductor because indeed the problem with this charge is related with the debye screening. And debye screening, basically it is here something like TC of the Fermi energy. And so better to have something, high TC is much better. But on the other hand, the problem with the surface with high TC. But if this problem can be solved, definitely high TC, like IPCO, could be very appropriate. Okay. And why it may be interesting? Simply, if you have a Josephson junction, okay, if you have Josephson junction, and we put nearby this Josephson junction the vortex, you can control the critical current of the junction. So, in fact, moving vortex, we can, let's say, switch on or switch off a Josephson junction, and you can use it for memory also for some many different applications. Okay, but also the question, if you have vortex, you can move it. But the question, if we can create vortices itself by the laser radiation. And the answer, yes, it's possible if you have very short pulse of the radiation, and due to so-called Kibble-Zurich effect if we have very fast transition through the critical temperature, a lot of fluctuation occur, and for example, one of the fluctuation is the creation, type of fluctuation is creation of the vortex-antivortex pair, and if they are frozen, in fact, it will be the frozen topological defect, it will be vortex-antivortex pair. And indeed, we can obtain this vortex-antivortex pair. It has been nicely observed and also investigated the different conditions, how you can obtain. But once again, it's not the solution of the final problem because it is vortex-antivortex. But if you want to work with some definite object, you need to select vortex here. Naturally, you can say that you can remove anti-vortex, but it's a little bit complicated story. And then we decided to look on the inverse Faraday effect. Direct Faraday effect, just rotation of the polarization plane. But inverse Faraday effect has been predicted first by Lev Pitaevsky. And it's related with the fact that if we have circular polarized light, in such a case we obtain the magnetic moment. And it's just in close relation to what has been said in the talk of Vitaly Yakovenko. And this effect has been perfectly, Victor Yakovenko, has been perfectly observed on experiment in some dielectric system, and we asked ourselves if it's possible to have this effect in superconductor. And indeed, we performed the first calculation using time-dependent Ginzburg-Landau equation, and considered what happens if we have superconductor in the electric field created by circular polarized light. And here it's very important point is that you should use the complex relaxation constant, because usually in superconductor it's a real relaxation constant and it's some sort of the decaying solution which occur. But if you add here the imaginary part, it's some sort of the oscillating. It's like Schrödinger equation it became. But in fact, it's some mixture of these two solutions. And indeed,
So the imaginary part refers to some sort of particle Hall symmetry breaking?
yes, exactly. It's present all the time, and it's related with the, let's say, dispersion of the electron spectrum. It's the same.
The sigma region is the sign of the charge in the Hall, the vertex.
Absolutely, the Hall effect, yeah. Yeah, yes, absolutely. It's my slide that I skipped. In fact, sorry. Sorry. Where am I? Okay. And in fact, we indeed obtained this current, but it's a small current, like in the case of Victor Yakovenko discussed. It's a small effect. And once again, we asked ourselves, is it possible to use this inverse Faraday effect to switch between state with different, let's say, polarization of the current, so on. And for this, I guess the best way is to choose the superconducting ring, nanoring. And for example, if you apply circular polarized light, you obtain current, which will be in this ring. It's okay, it's magnetic moment, it's fine. But once again, it's small. And if you switch off radiation, it will disappear. But if we use the same system, the ring, and apply external magnetic field, static magnetic field, we know that in this situation we have so-called little Parks effect. And critical temperature, for example, and the state oscillate as a function of the magnetic field in such a way that when we have exactly half of the quantum, the flux through the ring, we have the degeneracy between two states with orbital number equals 0 and orbital number equal 1. So we have, in this case, the degeneracy, but not coexistence. The system will be only in the state n equals 0 or only in the state n equals 1. And now the idea is to switch on the circular polarized radiation and to help system to choose between these two states. And more precisely, the same technique has been used. It's time-dependent Ginzburg-Landau equation modeling. For example, for each point, it was a realization of 500 cycles. And what we obtain that if, for example, we decrease gradually the temperature from above Tc to below Tc, in such a situation, we may obtain 100% probability to find system in the desired state. So it's completely controlled by the chirality of the radiation. Even more, you can do, for example, here it demonstrates that it's pretty robust against fluctuation of the, for example, flux through the system. But even more, you can apply the pulse of the radiation to the superconducting system. The pulse with rather high intensity, and if intensity is high, you destroy superconductivity, in fact. And you destroy superconductivity, but then the pulse here, it is the amplitude of the pulse. When the pulse decreases, the superconductivity intensity decrease will appear, but it will appear in the presence of the circular polarized radiation. And so it will appear in the desired state, n equals 0 or n equals 1. But these states correspond, in fact, to the opposite direction of the current. So it's very easy to detect these states. And even if you switch off external magnetic field, the system will remain in these states as a metastable one. And I guess more plausible for experimental observation of this effect, not to use single ring. It's possible to measure magnetic field, but better probably to use a system of the 1,000th of the ring and to look, for example, on the statistic of this switching. Okay, so I am now at my conclusion. First, we suggest a method of very fast single vortex manipulation, and I forget to say that it's really very fast. It's a nanosecond range. And then inverse Faraday effect may be quite efficient tool of the all optical switching. But if I say all optical, I use the laser terminology. But in fact, here, the characteristic frequency corresponds to the inverse TC, critical temperature. So it's better to say it's gigahertz or terahertz frequency, something like that. Okay, and finally, I hope that all this can open the way to superconducting optoelectronics. And yesterday, I was contacted by email by my friend, artist and cartoonist, and he asked what will be the subject of my talk. I tried to explain him in my reply of the message. And he sent me back his drawing, how he imagined this system, how he imagined this system works. Okay, so thank you for your attention.
Artificial intelligence. Thanks to the speaker again.